Okay, so Mikkel is also involved in the NOMAD project, and he's working at the Technical University of Denmark. And the topic is data quality and estimating errors on DFT calculations from high quality reference calculations. Okay, please.
All right. Yes, so I will talk about estimating and controlling errors in DFT calculations. So, as you see from this long list of authors, which I'm really standing on the shoulders on here, it's been really a team effort within NOMAD here. So, because it required calculations in different codes and so on, and it was actually relatively easy to do in this nice community of NOMAD people. Let's start out with some history. So what you see here is essentially the history of calculations on very simple material silicon. You see the lattice parameter as a function of time. History starts when PD was born, 1996, and we end up here at present day. So what you can see is that the lattice constant as a function of time here is there's some scattering. There's different values. When you look at 2016, certainly there's a lot of points here. So this was really a community effort where something like 30 codes or thereabouts was used to calculate the lattice constant, and you can see that the spread is at least a little bit smaller than it used to be. So that means probably we can be relatively confident that the distance between the calculated values here and the experiment is now not numerical problems, but exchange correlation inequalities. So this was published in Science in last year. Of course, people looked at more than just silicon for this science paper. So this is generally referred to in the DFT study, I think. So they looked at in 71 elemental solids with the PBE functional, and what one of the things they did was calculating energy versus volume curves, and then comparing two methods by looking at the difference in such two curves, okay, according to some measure which is called delta. So what this slide is supposed to illustrate is that codes, when they are sort of really converged with extreme numerical settings, much more than you would use in daily life, they can agree. So the green colors means there's a very good agreement, and in general this is the all-electron codes, so the most precise one, shows the best agreement with each other. And the yellow stuff is PW calculation, solar potential calculation, and the red ones here, which are principally bad, are some old solar potential calculation that nobody does anymore. Okay, so in principle, one can get these codes to agree with each other, but you have to use really high numerical type settings, like really high basis set and so on. So this is good, but if you think about NOMAD, and also daily life with DFT calculation, we don't use these settings. So we use final basis set and final. If you look at a solid K1 set, you know some. So let's just take a very simple example. Let's say you were looking at in the NOMAD repository, you find two materials. This is the same material but two different phases. I call it T and H, so this is molybdenum disulfide. And then you can ask the question, if you look up in the database, which one is the most stable? Okay. So that's very easy. You just look at which one has the lowest total energy. Let's say, right? So you subtract these two numbers and figure it out. But what happens if these two phases were calculated with different settings? So one was sort of a crude calculation, one was an accurate calculation. I mean, can you then compare these numbers and so on? So this is sort of generally, I think if you search in NOMAD, you can get a lot of data, but how can you compare them, or how much you can trust these numbers and how can you compare them? So, and of course, numerical settings are many things in codes, but we'll just focus on basis set and Williamson sampling in this topic. And of course, if we have some information on these errors, we could feed them into everything you do on top. Like machine learning, you can have include that you have some uncertainty in your data that you try to fit on. Or you can simply say, okay, I'm only interested in data with a certain quality. So you can discard, let's say, everything that is not converged within 25 million electron volts or whatever you like. And of course, this is nice. We will look at actually calculating these errors, but of course it would be much more practical if you can also estimate them, because you don't want to calculate these errors for all 44 million entries in the numerical database. So this is what I'm going to talk about. So this is the rest of the plan here. So first, what materials or what data set did we look to take to do this higher accuracy calculation for, and then look at errors. And when we these two sources of errors like weighting set and K-point sampling. So I'll talk about errors in total entities and relative entities. We looked at much more, but I don't have time to talk about that today. And then this is just looking at how it goes for the codes, and then we will try to do some simple estimation of the errors. And finally, there's a bit outlook of the other part of the error there, which is not the numerical, but the exchange coordination error. And then conclusions and a little bit about this analytics error bundle that we made if you want to go in yourself and then play with all this data. So what did we look at? So we took the 71 elemental solids from this density T study and extended that with some binary solids. It was 82, so there was Bjorn, who was part of it here, who sat down, looked up in Springer materials for experimental binaries, generally took the most stable ones, and then we selected 82. And then in the end, that's a sort of so these were sort of selected by us. So as a kind of a test, small test data set, we took 10 random ternary solids from the numerical database to test what we found in the end. And that's already the thing. I said we will be looking at total energies and relative energies here, where relative energies is energies between a solid at equilibrium and expanded by some percent, 5%. So we have to do the calculation with some codes, and we chose these 4 codes out of, let's say, the 30 codes that's supported by NOMAD. There's 2 all-electron codes, 2 pseudo-potential codes. So the reference basis was basically chosen by the experts or even developers of these codes. So if it's IAM uses atomic-like orbitals, if you know this code, it's called Tier 2 basis set as a reference. Here's the pseudo-potential code, with plane waves. You use 1600 electron volts as the reference, and VASP is a little bit different. It comes with a recommended plane wave curve of each element, and maybe took the reference at 200% times this, which should also be very accurate. All right, so of course when we look at errors, so this is just to give you some concrete examples before we go into the statistics a little bit. So if we look at an error from basis set first here, we're dealing with solids, we're dealing with rock states. So this is plane wave times a semi-periodic part here, and the semi-periodic part we can expand in some bases. So if it's IAM, should be atomic-like orbitals. If it's a pseudo-potential plane wave code, it's plane waves. So just to write a complete expression here, plane wave basis set here. And the size of this basis set is normally truncated by looking at the kinetic energy and defining a cutoff energy where we include all plane waves below this kinetic energy cutoff. So here I've brought 2 concrete examples. This is called oxygen. How the total energy converges with the plane wave curve. So you can see that oxygen starts up very high. This is a logarithmic scale, so this is exponential dependence. It's the same for gold, but it starts much lower, and they sort of end up more or less very close to each other here. The reason why oxygen is much higher is that it has more localized states or more rapidly varying states. So it needs a higher plane wave curve to convert that result. So this is just 2 simple examples. I should say that you can see the energies, they really vary by 4 orders of magnitude when you do this conversion. Starting at something like 10 electron volts and going below milli-electron volts. A really large sort of energy changes you're talking about. So now this is the conversion script. Oh, sorry, this is looking at the K-point sampling. So if you want to look at some observable and you have a periodic system, you have to do an integration over the Bouillon solve, which we approximated with some finite K-points. And if you do a uniform K-point sampling, you can define a parameter here, which is sort of the distance between your points in K-space. So the higher the value, the more K-points you have. So this is a convergent parameter. And now we can look again at these two same elemental solids, gold and oxygen. And you can see that of course it decreases and it looks like it's exponential again. But now the roles are reversed. Gold is on top here and oxygen is below. And that's of course because gold is a metal, so it's harder to convert the K-points, and this oxygen is insulated. And again, you can see that that is sort of orders of magnitude change in energy. Okay, so that was just some simple examples. So now let's do a sort of basic statistics and averaging over all the materials. So what you see here is error in the total energy for these elemental solids. There's 4 panels. Each panel corresponds to a code. And there's two lines in each panel here. One is the mean absolute error, and the other one is the maximum error. So the maximum error has a label on it, this element that has had the largest conversion error. And I should say this is a function of basis size here. So what we can note again that it's kind of across all codes. It's kind of similar that you start out with an error around 10 electron volts, and you go down below 3 electron volts when you do conversions. This is with respect to some reference we have chosen, of course. So if we look at also relative energies, we can say that, so this was the energy difference between an expanded solid and a solid in equilibrium. We can say that, so then you see the same curves as before, but now there's 2 new curves, this is blue and purple, that the error goes down by an order, 2 orders of magnitude for these relative errors because of some error cancellation in the basis or in the structures. So want to have some numbers and consider everything what people would say minimal basis, that you can get the mean error below 1 milli-electron volt quite fast, and we don't want to worry about anything smaller. At least I don't. All right, so this is the last slide of just looking at the errors. So here it is looking at the K-point sampling. I don't want you to look at all the details, but you can pick a favorite color here. So, for example, that would be blue. If you look at all the blue bars, so they have the same height. So it means that all the codes have the similar average error with respect to K-point sampling. And this is also what you would expect. And then that's good, because it means that if you know the error calculated with some code or some basis set, then you can already transfer it to something else, another code or another basis set. So let me just try to wrap up these observations here. So it's the same data, just plotting in a slightly different way. So what you see here is a percentage of materials that are not converged to a given criteria as a function of the criteria. So just to take an example, let's say I'm interested in having convergence criteria of 50 milli-electron volts. What can I expect? Well, then it turns out that 60% of your materials are not converged if you use a bandwidth of 400 electron volts. So it means you're left with 40% to study if you really want to have this criteria fulfilled. You can say, I'm not happy with this, I want to increase the bandwidth cutoff. If you increase to 600 electron volts, then you can see now it's only 20% that's not converged. happy now, and you can continue with all the 80% that are converged. You can do the same with the K1 sampling, but I will skip that. All right, so that was just trying to get a feel for the errors, so they can vary by orders of magnitude. So let's try to see if we can predict them in a simple way. So the first two equations here are just definitions, basically. This is the energy of an atom A with some basis set small b, and then that should be equal to our reference energy, and that we can make it by adding some corrections. So this is the error, essentially. We can write exactly the same expression here for let's say, binary. So the error we are interested in is, or I should say, we're trying to use these elemental solids of the atoms, basically the errors in atoms, to try and predict the errors of the binaries or any other material. So we can calculate this error, of course, and we do that, but we would also like to try to make an estimation. We'll do some more advanced things here, but we just took simply saying that we add up the errors from atom A and atom B in this simple linear combination. So of course we can do more advanced things, but this is what we did first. And just to give an idea why this might work, you can consider something like a heat of formation, which is an energy difference. If you insert the estimated error here, it turns out that the error we make on this estimate, on the estimated error, so to speak, is the basis set error on the heat of formation, and normally we expect these to be small errors because error cancellation for the heat of formation. So hopefully we can predict some errors relatively good in this way. And this is the plot we see here. So this is the estimated error versus the actual error. And you can see that there's some correlation. The different colors here are different basis sets, and especially TIBO here, it looks like it's a pretty good correlation. So let's try and zoom in a little bit on TIBO here. So if you start in the inset here, so this is where I plot the actual error minus the estimated error. So it means that if there's a lot of points around 0, so this is good. It will do a good estimation. But you can also see there's something that is more far away, like 100 millimeters away. If you make a histogram of this plot, this is you see the main figure here, then we can assume this is sort of a Gaussian and has a standard deviation of 50 millielectron in this case. So what does that mean? So that means, for example, that we can predict this estimate of the error with sort of plus minus 50 millielectron volts. So of course, what is the actual error? So this was done at 300 electron volt cutoff. So they sort of the average error is 1600 millielectron volt, meaning we're trying to predict some error on the order of electron volts with, let's say, 50 millielectron volt accuracy. I think that's pretty decent. So here is kind of the test set. So it says binary up here, it's just ternaries. So this is just 10 systems we took randomly from Nomad. So with the same people on that, and again you see a simple prediction is work to some extent. Okay, so now let's try and take use these errors for something. So let's say I've looked at this phase of inverse 2, calculated with the cutoff at 300 electron volts, and the other phase was calculated at 800 electron volts. So then I made a small back of the envelope calculation here. So here's just the total energy. It doesn't really mean anything, this number. The total energy here, and we subtract and we get half a volt. So this suggests that the H phase should be more stable than T phase by half a volt. But this was for different bases, so let's try to add our estimated corrections with error bars. So T phase was the bad basis set, so that's a large correction. So a relatively large error bar here. And in the end, if we go through, we find that we can estimate, we get an estimated energy difference of 4.9 volt, which is pretty close actually to the reference calculation, and we have this error bar. So I think this probably say this is certainly the most stable case, even with these very different basis sets. All right, so now let me change gear a little bit. So this is going away from the numerical errors and into the XC errors. So I'll assume that all we have converged over our calculation with numerics and just looking at the exchange condition errors. Of course, one can think about doing this in different ways with machine learning or advanced data analytics. And one approach is this has been done at our department is using a Bayesian learning scheme, and it's just refer a little bit to it. So it's essentially you take an example of enhancement factor. So this is the green curve. This is what defines the DTA function. So you can see one curve here is PVE and one is RVB, and then there's this ensemble of curves here. And then the width here is chosen so that you, when you do a calculation, you can get error bars on your observables. So what been previously done is people have really tried to plot the new functionals. We are not interested in that. We just want to predict an error bar. So what we do is that we make sort of ensembles here where I say PV is the mean. Okay, and then when we use that and do some fitting to experimental data to come up with some error bars for all DTA, PV, RPV. So here's an example taken from the. Sorry. So here's one example taken from this paper here. So if you do the calculation, let's say the piece affinity with all these functionals, you get this large spread of values. If you instead do the energy difference between BCC and FCC, this is for copper, you get a much smaller spread. So you can see that the estimated error on the cohesive energy is like 500 millielectron and the BCC minus FCC is only 5 millielectron volt. So even there are some quantities with DFT, there's a large error, you can even, there are some that are less. So this is what people also find with compared to experiments that actually works, and you can say this estimation works in this case. So now we try to apply this to the binaries. So what you see is the experimental heat of formation versus the calculated heat of formation. Now with error bars on, and you can see that some of the error bars they incorporate the experimental one. Well, here you just see this just to get a feeling for the spread of the error bars. So there's sort of estimate error sort of 200 millielectron volt from the DTAs. I should say that DTA is very simple, so that, for example, this system up here is very far off, and we don't do a very good prediction of the error bar, but this is, as soon as you have some physics that's not in DTA, it will also be van der Waals, then you cannot really probe it with this ensemble of functionals, and you cannot predict a good error. So I think that's okay, because if you could do that, you probably also know how to make a much better functional. So this is just a little bit of statistics. So if we're doing a good job on the error estimation, then this blue histogram should look like a Gaussian, and there's some systematic shift, and there's some tails up here which come from the physics missing, but overall it looks okay at least. All right, so let's return to silicon before we end here. So we sort of established that the numerical errors here are probably well converged. So here I've tried to add this error estimation on the lattice constant of silicon. You can see that is actually pretty large, and you can incorporate the experimental values, so at least in this case, overlap the experimental error bar. And it's much larger than the numerical error, and that's where we want to be. All right, so this is the conclusions. So I talked about that you can basically say, okay, control and predicted reasoning load with this simple scheme using the atoms. We looked at the K-point sampling errors. The good thing is they are comparable across code. They're pretty hard to estimate. For example, metals are very different from semiconductors, so you do that just from the elements. You would have to know about the bank error and so on. And then finally, there was this outlook on XC errors, and they can be estimated, but of course it doesn't work if the physics is not really proved by or included in the GTA. So finally, there's some acknowledgement here. So this is all the people that helped out, and thank you for the attention.